shear transformation. So this is this interesting transformation in computer graphics where you don't really see a transformation like this in the real world. At least it's not that obvious as rotation and scaling perhaps were. So an example would be like this. So we have again the same geometry, and when we change these sliders here, it kind of shears or tilts to this one side. Or alternatively, we can do a similar thing this way. And what does it do is it kind of shifts or shears everything parallel to the other axis. And you can also notice that the matrix again gets a bit complicated. And here are some diagrams. So we can distinguish two shears in 2D, shear X and shear Y. And we can kind of describe it as it tilts one of the axes parallel to the others. Or if you can think about like if you have a stack of playing cards or books and you kind of push on them, then they kind of all move parallel to the table they're on, but kind of tilt to one side. So it's kind of shared or tilted stack of cards. As for the basis vector, well, if we do shear Y as it's shown down here, then we move this first basis vector parallel to the Y axis. And you can notice over here that its size also changes. So it's no longer of unit length, but well, in this particular example, it's already square root of 2. And if we were to shear it even further, then it would get even longer and longer. Of course, we can read out the matrix from this basis transformed basis again. So it's 1, 1, because the first basis vector is now at coordinates 1, 1, and 0, 1, because the second basis vector stayed the same. And notice that if we put different numbers down here, then this affects the amount by which we shear. So for example, if we put 2 here, then this vector would be 1, 2. So it would go up here, and this parallelogram would be even further skewed or shared along the y-axis. We can have a more rigorous definition perhaps. We can define this by the angle by which we kind of rotate or share this basis vector. So if we define this angle here, we could say that the shear y transformation would be 1 and the tangent of that angle, and 0, 1. And the coordinates will get transformed like this. Or we could define the shear x similarly, so that the x coordinate would be just added the tangent phi times the y coordinate. And you can think about it and imagine that now the larger the y coordinate is, the more the x coordinate transforms. And we can also see the shear transformation in 3D. And we can define it by the plane in relation to which everything moves parallel to. If we shear in relation to the xy plane, then we have tangent alpha and tangent beta up here in these elements of the matrix. And now you can imagine there's two angles. So if you have a plane, you can shear it in one angle along one of the axes and another angle for the second axis. But everything still moves parallel to the xy plane. Because you can see in the result, the z coordinate of any given point stays the same. So if z is somewhere and we share it along, well, the x or y coordinates or axis, then z stays the same. It kind of moves in parallel to the xy plane. Now from this video, you should understand the shear transformation. It shares the space from one axis. There are different shears depending on the axis, so shear x and shear y. You should understand these matrices, so if we put elements in these corners or in these columns here, or this column here, then it does the shear operation. And in 3D, shear x, y is like this. Now, it does have some usages. It's not just a mathematical curiosity here. We will see some of these usages later on. And very often you usually don't do the shear by just on the objects. If you do some modeling in Blender, you don't have like a shear transformation. You have scale and rotation. But it does become very useful in different algorithms. For example, if we want to do shadows, and one of the tasks you have is projection shadow, where if there's sun coming from one angle, you kind of want to share the object from that angle and then squish it down to the ground plane, and this will be its shadow. But we will see these things later on, and we will see very soon that understanding this shear operation is a key to understanding how translation, how moving things in 3D actually works in computer graphics.